Hi, my name is Ray Konopka, and in this session we'll be looking at effectively using generics in Object Pascal. Before we get into the mechanics of using generics, consuming them, creating our own types, we need to have a little background first. We need to understand exactly what generics are, what role they play, what benefit they give us to our source code, and more specifically, what do they look like? What's the terminology? How do we name these? How do we identify the syntax so that we can understand exactly what we're looking at when we look at the various code segments? Of course, then we'll follow it with a good long example of consuming various generic types. That's the most common approach when we start using them. And then we'll finish it up with creating our own generic types, which really leverages some powerful capabilities. So what exactly are generics? Well, more technically, they're called parameterized types. That's because the code that we're going to create will use placeholders instead of real types for where it's necessary. As a result, these placeholders get used, they're parameters, instead of real types. So it's type agnostic. We don't really care about that. It's generic, which is where all this comes from. However, at some point we do need to replace these parameters with real types when our code is going to be used. And we'll see exactly how that happens in a minute. Before that, though, we still should have an understanding of why it is we want to use generics. What are the benefits that they give us? Well, first, let's look at what we run into when we don't use generics, where it's very common to treat everything as a T object. I mean, if you listen to the object-oriented theorists, that is the way. That's the best thing ever. Is everything is an object. We can just put anything into a list of objects and everything will just work happy. Well, in practicality, that isn't always the case. We have a type safe language, but we lose some of that. We don't know exactly what we're dealing with when we treat everything as an object or as a pointer. The sample code on the side there, I'm sure we have all of, each of us has one of these in our little toolbox of managing a list of integers, or whether it's a list of doubles or some other list of customers. We descend from a T list and we typecast everything, create public versions of the various types that we want. And if we have another list of a different data type, we copy the whole thing over again. It gets a little crazy. We're typecasting all over the place and we lose all the type safety benefits that we get from the language. So generics give us the type safety, both at compile time and runtime. It allows us to reuse our code, logically speaking. Now technically, when we talk about creating a new type, the code is defined once but will get duplicated in memory, so there is an impact of it, but it's negligible compared to the benefits that we get from the reuse of the logic that we're dealing with, the elimination of the types casting that's in there, and frankly the code is just clearer once we understand how to read the generic syntax. So that's what's next. So taking a look at a typical example, the type definition that we have right here is for a new class. It's a parameterized type. The angle brackets are used to reference the parameters, the parameter list, if you will, for this type. So the type itself, the parameterized type as a whole, is called tsample of T. The brackets and the T are included in the name of the type. So it's not just tsample. That would be a different type, non-generic type as well. So tsample of T is the parameterized type. The type parameter, so switching the two things around, but the T value is what is going to represent some real type once we do the substitution. So for now, it's just any type is what that's going to reference. Now, in order to use this generic, we need to replace all of the parameters with real arguments, with real values. So here we have tsample of T, where the T has been replaced with integer. Well, now the type tsample of integer is a constructed type. the type parameter of t was replaced with a real type, the compiler knows exactly what that is, how to deal with it, and it can construct all the code necessary for this particular class. And now S is a type, or is an instance of that type. So that's really all we need to know with terminology. But there's 4 key pieces there that are there. The RTL has many pre-built generic classes interfaces that we can leverage, and this again is the most common way to get started, is to use the generics.collections unit. So typically you'll see t-list and t-dictionaries. We'll also use the t-object list of t, the t-object dictionary of t-key and t-value. Those are the 2 examples that I'm going to be showing. But we'll also see an example of iComparable a little bit later on, which is a generic interface. So we have all of these throughout the language. It's really powerful. So let's get started with some actual code. So here we're in XE7, and I have a little sample application that's going to help us describe the various ways we can manage a list of baseball players. That is our task today. We're going to do the same thing in all 4 examples, but we're going to use a different data structure in order to do it. The first 2 I'm going to go through rather quickly. We've probably seen those before. Certainly the string list, we use that all the time. We'll look at the object list quickly, and then we'll look at the generic counterparts to those, and including the object dictionary, which is very cool. So to start, let's dig into our code. And as I mentioned before, managing a list of players on a baseball team. Each of these routines that we're going to do does the same thing. It's going to create the team using whatever data structure it had at hand, add some players to it, try to find a player, display some info, and then continue on. So first thing that we do is we create our t-string list to add for the new team. We're going to add 3 players. We have a class that has been defined earlier called t-baseball player. It takes a name, a position, and the hits and at-bats. We can figure out batting average and things for that. In addition, the string list allows you to have an object with each item in the string list, so we can do that. We just index it off of the player's name, and then add the new player reference to it. Now technically we've got a reference to the name. We also have a reference of the name inside of there, but we can look past that. After we've added the items to the players to the team list, we can use a function to find the player. And a typical way to do that is, and I'm using a function here, is we take the name of the player and we simply use the find function, given a string, and then it gives us back an index, and if we find that player, and then sure enough we will check to see if we actually have that. If the player is not found, then find returns false, and we return back just a result of nil then. So from there we can find the player, display the message, and what it is we are interested in. Likewise, when we want to iterate through the team, we have to go through and 0 to the count, -1 of the team, and display the message. Now the thing to note here is that we will have t-baseball player having to typecast the objects that are inside the list. That's because the objects array is just an array of t-objects. It doesn't know anything about stats. Which is a method that will return back information about the player. And of course, because we just add these objects to the list, we have to clean it up. So we have to, before we free the list itself, we have to free each of the individual players out of the list, and then we manage that. And so if we give this a quick run, we can see what it is that it does. And so as you can see, we're doing the string list version, we found the player, and then we display the active roster. Pretty straightforward. All right, let's take a look at the next version using the object list. So below this, on our functions here, we have the object list click. And in this example, we do the same set of statements, of commands, but instead of using a string list, we use an object list. Now the nice thing with the object list is that it knows how to handle objects, so we can eliminate having to free them up, but there isn't a whole lot more benefit that we get from that. We still add each player like we did before. We can still do a find player. However, the find player has to be a little bit different, just because it doesn't have a built-in index function. So we end up mimicking what the index function does by comparing the passed-in name with each team member name that's in there. Of course, again, because we're just dealing with T objects, we have to typecast everything and to get that to work. But once we do it, it will work. Likewise, continuing on, we find the player, display the message, and then we can iterate through the team. And so if we go ahead and give this a run, we're going to come back to the comments in just a second. So if we go ahead and run the object list, we see we get our exact same output that we would like. Thing to know is we just free the list. We don't need to free the players. That's great. However, we can still run into problems with this. And so, for example, let's say I would like to do the for in. I have an object list. I know that I want to iterate over the whole team. And it would be really nice to be able to do for player in team do this. So if I were to comment out these two statements, go ahead and try to run this one, what I get is an error. And I get the error because T baseball player, which is what the player is defined as, is not equivalent with the team. The team is an object list. It just has a pointer that references the iterator, and so we can't use this syntax, which is a shame because it would be really nice to be able to do that. With generics, we're going to, so that's one of the next things that we'll look at. So if we go back and comment this out, and the next example that I want to show is what happens when we can add anything to the list. And this is one of the downsides of just dealing with objects. Now, we technically wouldn't do this on purpose, but we've all been there where we've had a list of things or an object reference to something and it becomes nil or it's got the wrong data type on it. And as what we'll see is the compiler will have no problem at all compiling that the code. It's just an object, so it's a T button. It doesn't matter. It still descends from an object. We can go ahead and add this in and we get a floating point operation error. And the reason for that is because it's now trying to evaluate that stats, but it's not a player. It's a button. It doesn't know what any of these values are. And so we've totally messed up what that code is supposed to do. And those can be rather tricky to track down. So ideally we want to eliminate that. So let me bring both of these, comment them both back up so we can move on to our next example, which is using the generic version of the object list. So T object list of T. Now again, the parameterized type is T object list of T. That's defined in the generics.collections unit. However, in order to use it, we have to construct one. So we're going to construct a new type called T object list of T, or T object list of T baseball player. So T baseball player is a real type that we've defined. We're going to use it as the elements of our object list. So this object list, team, is defined as this new type. Team will only be able to hold T baseball player references, which is great. Makes it a lot easier for what we want to do. So, going back to our steps, to construct it, we just reference the type name .create, just like any other reference type that we have. So we construct the team, we add the players to it, we then find the player. Now the find player is pretty much the same as it was before. We're locating the player by name, but now we can actually go through the list and find, and without having to typecast everything, because we know that team of I is going to be a T baseball player, so it will have a name property, so we can reference that. We can return back that same baseball player as the result value. So it's a quick way to do our find. Display our messaging. Now we can use the iterator over it. So for player in team, display the player, which is great. So, and then of course, because we're an object list, the list will manage the objects for us, so we don't need to do any cleaning up. Let's go ahead and run this real quick, and we see that yes, it does do our correct output. So great. We've eliminated some code. We've made it a lot clearer. Well, what's even cooler is that let's go back to that example of adding the button in. What happens if I try to add a T button into my team? Well, the compiler tells me that is not compatible. It has to be a T baseball player type. So this is great. So we've gotten some clarity in our code. We've eliminated some of the typing problems that we run into because of dealing with just T objects, and we've simplified the logic. Well, now let's take it one step further and look at a class called a dictionary, specifically the object dictionary of T key, T value. So a dictionary is a list that's managed like a hash table. It's managed by a key, and you index the key to get a particular value back. Well, that's perfect for our little baseball team here. So again, we need to construct the type, and so this one is going to be T object dictionary of string T baseball player. And it's the whole thing. It's a mouthful, but that is the constructed type name. So in order to construct our team, we need to reference the whole value. Now, one of the little nuances of the constructor for the object dictionary is that there's a parameter that you need to specify if you want the dictionary to own the objects or the values. What that means is that when we clear this up, we release it, we want it to free up all of the things that we've added to it, all the value references. So to add the team, there's an add method to add to our dictionary, and it takes a key, which happens to be a string, which great matches our name, and the actual player, which is the object that we're referencing. Do they have to be part of the other? No, not at all. They're independent things. So I've added my items there. Now this is really kind of cool. This is the equivalent to find the player. Well, the dictionary knows how to search on keys. So to find a particular player, we just reference team.items, passing it an index, but is a string, which is really cool that we can do this. So this will return back nil if the object is not found. If it is, then it's not nil, and we can reference it directly. No typecasting at all needed because we're only dealing with T baseball players. So we got rid of the whole find player function completely. And of course, we can iterate through by a couple different ways. The most common when you're dealing with a dictionary is to use the keys. So we can iterate over for K in all of the keys. Well, the keys in our example here are all the names of the players. So for each player name, we're going to index into the dictionary and get their stats. And of course, we just free up the list. This is the cleanest of all of the ones that we've dealt with. And so now when I go and run this, everything is all exactly the way I like it, without the extra typecasting, without the extra find functions, and we can enumerate over everything very clearly. So next up, let's take a look at how do we create our own generic types. The easiest way to get started when we create our own generic types is to actually start with a regular class, a regular type that we're dealing with. Now typically generic types are classes. That's really where you have the most value and using these to substitute, because you're operating on some other data types when you're working with these. So what I like to typically do is just define the class as normal. Now you might want to use strings or integers to manage what you need to do, and then we can then convert it into a generic version by substituting the data types that we're referencing. And as I mentioned before, the convention is to use T for your placeholders. If you typically, if there's just one, you will do that. If you have multiples, then you might reference a name so that it's a little clearer as to what you're dealing with. So the dictionary version uses T key and T value. But it's pretty straightforward. So let's take a look at some code to see what makes all this work. So the other example that I've got is I've got my generic list, linked list, and I'm going to do a canonical example, which is pretty common for learning how to work with generics, and that is building a linked list. And we've all done this back in our programming days. Simple, node definition. It's going to have a data payload that's then going to have a reference to another node in the list. So pretty simple. What I like about this is that it really captures home. It's simple to construct and visualize, and then we can see how we plug in T to all of this. And the only thing that's really different is every linked list is exactly the same, except for what data payload is being used and what it's pointing to. And so we're going to see exactly how this connects together when we use the generic version. So instead of just defining it as T node, we're going to call this T node of T, meaning this is a parameterized type, and T represents some data type that we'll define later. Well, the pieces that we need is we need a piece of data. What's this node going to hold? Well, we're going to call that private instance field fdata, but its type is going to be T. So whatever we instantiate the parameterized type with, how do we construct it? If this is an integer, when we create the real type, then fdata will be of type integer. If this is T customer, then fdata will be of T customer. Some real type. The next node reference is a reference to the same type as our parameterized type, meaning it references a T node of T reference. Again, the same thing. You substitute it in, that's what it'll refer to. To construct it, we have a special constructor that takes the data of type T, and it has the next node, which is of type T node of T. So we'll chain these. So when we add a new node to the list, we simply create it and connect it to the next one. And we can just keep chaining them all along. There's a toString function that we'll take a look at to give us some interpretation of what we're looking at. And then the property values, to be publicly accessible, we can also use the same substitution. So property of data will be of type T. So let's take a look at our various examples. So we'll look at the implementation of this. And so from here, I'm taking T node of T and using the same constructor that I defined before, calling inherited, because when it gets constructed, it will be just a regular type. So we still have our inherited create. We call that, allocate the memory for it, and then we're going to populate the initial values for data and fnext for what's passed in. The toString function is a little helper function that uses the T value type, and T value is, you can consider it as a lightweight variant of the variant type. It serves different purposes, but it allows you to do some of the equivalent things. In this case, what we're doing is we're going to convert the given data type to a string. So whatever the value is being held by fdata, and we don't know anything about that at this point, only that it is going to be of type T. T could be integer, T could be T customer, T could be T baseball player, we don't know. However, if there's the T value knows how to convert it, meaning convert from T, then we will actually get the string representation from that. So this is a nice little helper function to do. T value is part of the RTTI, and I have another session going on about using advanced RTI inside of Object Pascal, and I will cover this in more detail. So let's take a look at a first example, which is to have a linked list of scores. So what I've got is a I have a test scores and I have an individual score, and they're both of type T node of integer. So I know that my linked list node is going to hold an integer value and point to another node has an integer value in it. So let me go ahead and run through this. So test scores is getting created. It does not have a next node, so it specifies nil. The first test score is 85. We set test scores again to a new node. It has 95 as the score and is referencing the original node. So again, very common linked list chaining. I'm simply updating the head of the list as I go on, and I can rip through all of those should I need to, which is what I do next. So here I'm actually figuring out what the average score is by going through, starting with the first at the head, going through the list until I'm done. So again, score.next, score is of type T node of integer, and so score of next is still the same data type, and so I can chain through all of my pieces. Once I have the total and I have the number of tests, I can figure out what the average is. So let's take a look at what this one looks like. So test scores, here we go through, we just rip through each one, displaying it, and then displaying the value. It's pretty straightforward. So next up, let me go into doing the same thing, except this time we're using a T node of string. So same logic that was done before, but we're just going to iterate through and build up our list using strings as our data type when we construct each instance. So we're building up a sentence, we can iterate through, still go through the word next, the word.next, and this will allow us to display a sentence at the end. So let me go ahead and run this real quick, and effectively using generics in Delphi. So we have that same ability. So next up, we want to take a look at some other interesting information or techniques that will help us use generics more effectively in our code. One of the interesting things that we can do with generics, we've talked about building new classes with them and the parameterized types that are referenced in them. However, we can also apply the same concepts to a method signature. And this is actually pretty cool, because not only can a method be part of a generic class, a generic method can also be part of a non-generic class. And this sounds a little weird until we see some practical examples. So let's do exactly that. So in this third example program here, I have a utils class that I'm creating. It's not generic, but it is simply a placeholder to manage a number of utility functions that one could create. Now these are class procedures, so I don't need to construct an instance of the tutils class in order to use them. It does help us that way. And so what's cool about this, though, is that I'm actually defining these functions as generic functions rather than a type that's associated with it and having to bring along all of that. And so specifically, what I've done is I've created a swap of t and min and max of t. These are very common things that I will need to use, and it makes sense to have them connected to any type of data type that I want. And so if we go and take a look at how this is implemented, it's exactly what you would think it would be, except that the two variable parameters are of type t, and the temp value for the swapping is of type t. The min and max functions are a little bit more interesting because they're using an interface reference. This is where that I comparer of t came in before from the earlier slide. Here we need some sort of comparer to be able to compare whatever data type that we're using. Integers is fine. We also have strings and things like that, but other objects you still need to be able to compare them, other types that we would need to have passed to us. So we use that to do an actual comparison, and if it evaluates to less than 0, we go ahead and return back the right value, and if opposite for the max, we just check if it's greater than 0 and we have our functions. So let's see how we can use those in our code here. So very simple application. We've created a couple different variables that we're going to use, some strings, some floating point numbers, integer values, and so if we wanted to find out the max for a set of integers between x1 and x2, we would simply call tutils.max of integer. Then we can use the tComparer class, which is defined for us, and that has we can specify its t as being an integer type. By doing that, and we're using the default comparer for that type, then this will work just fine. We can do the same thing for the max double. Likewise, for doing the strings, we do the same thing. We can do a tComparer string default, or we can even use the tString comparer using it on the straight ordinal value, which would be different between the two if you want case sensitivity and things like that come into play. One of the things that's also very cool when we're talking about the use of generics and these various types of functions that are in place is this next example is using the max integers, but is actually using an anonymous method, no named method, inside of the comparer. So when we're going to construct a new comparer object that deals with integers, but we're going to put the code for that directly inside the call here. And so we start getting some extremely flexible ways of managing our data types and the functionality associated with them. Now again, this is rather contrived since we're simply finding out the max version for the two, but this does indeed work quite well. And then of course to do a swap, we can simply swap the string values, passing the two values in, and it will work just fine. So let me give this a quick run, and we can see what values we get back. And so we've swapped our first and last name, we've got the anonymous values, and all of the different sorting and comparisons come into play. So to wrap up, we have a couple more things to talk about with respect to generics that you need to be aware of. The first is constraints. We've talked about just a basic T, the first example here, that okay, T can be any type. Well, that's great in theory, but in many cases T can't be any type. In order to write the various code that you want, it may be sufficient to say that I need this to be any reference type. So anything that's a class, then I can go ahead and use that. And so we can put a constraint on T that it has to be a class. So we can't put an integer in here because we may be calling the create constructor on it. Well, that's actually another constraint. If we want to call create where it has to have a constructor available, then we would use the next one, which is the constructor. So this is hand in hand with the class. So if it has a class, great. If it's a constructor, that's what I need. The record means that it's a value type, and so it could be a record or any other type of value type. You can also specify a real base class, so it has to be this base class or some descendant of it. So it doesn't have to be just any class, but you can restrict it. What's also nice is you can restrict it based on an interface. So you can specify some, ISOM interface or IComparable, IEnumerable, and so forth. A lot of flexibility in there. You can even do a generic interface and have some complicated restrictions there. Last piece, one of the things you might often find is when you're dealing with T, these type parameters, because they can be different types once you instantiate them, your coding logic may have to require or may need the default value for that particular type. Default value for a class reference is nil, a default value for an integer is 0. They are not the same. The RTL gives us a pseudo function called default, which when we pass it a type parameter will actually give us the corresponding default value so that the comparison will work. So if we wanted to save the file, but we only want to save a value if it's different than the default, we can do something like, if f field is not equal to the default, then go ahead and do that. The comparison will work correctly, and we don't have to worry about trying to figure that out another way. So that is all the information that I have today. My contact information is listed up there. The session material, so all of the sample code is all available at on the Raize website in the sessions directory under delphigenerics.zip. You're certainly welcome to download all of those, give them a try. At this point, we will switch over to the live Q&A and hopefully answer any questions that you have. Thank you very much for your time.
Okay, so you've already answered some of these questions here, but I'll go ahead and go through some of these. Is there available a generic version of B tree lists like TurboPower's SysTools TS tree?
I don't know the answer to that. I've not come across that in the generic collection class, but it's possible someone else has created something that mimics that functionality, but using generics for that. Certainly should be possible. I'm just not familiar with one.
Yeah, there's a few generic collection libraries I've seen around, but I'm not sure if they have those in it or not. It's probably possible to create one. Either way. Are there other ways to find a certain object like binary lookup? I'm guessing
Sure.
from a list?
I guess I'm not quite sure if the question is could you write something in generics that would allow you, that would facilitate that, or is there that functionality built into the generics collection classes for that? The first part would certainly be true. I haven't run into any data structure or algorithm that really can't be leveraged with generics if it makes sense to. There's a question coming later that may qualify this response a little bit more, but in general, if you have an algorithm that's, that makes sense and that you want to handle it for different types, different data types, then generics work very well in that case. Is there a binary lookup process, or class structure inside of the generics collection class? I don't believe so. Now, yeah, I don't believe, not in the traditional sense.
Could you make generics that uses another generic class as its parameter? So a T list of a T list of T, maybe?
Sure, you could. Actually, I guess when my first initial response for that was you do something like that when you're dealing with interfaces quite frequently, where you're defining one generic class, but you want it to support an interface and it's using this usually the same base type. But if you were to extend it to where the type parameter for the generic happens to be another parameterized type, could you do that? Yes, you could do that. The same rules would apply when you go to construct it. You still would need to substitute each of the different type parameters with real types. Once you've replace your T's with your strings, integers, and so forth, it should expand out quite nicely.
Okay. Are there examples of bidirectional lists? Yes, I'm guessing bidirectional linked lists.
I don't have any one in the sample code that I'm doing. I'm not sure if there's any that if somebody's done that out there. Be a good search to try to see. One of the nice things with the generic syntax that Object Pascal uses is that it is very similar to the syntax that's used in other languages, namely C#'s generics, even the generics in the new Swift programming language from Apple uses a very similar syntax, including specifying the constraints and so forth. So if you search for a generic bidirectional list, you may find some example code that illustrates that. Unfortunately, I didn't have time to put something like that together in this session.
Okay, good point about finding some other languages and adapting if you need to. Keith says he wants to create a T-tree view where each tree node owns a yet-to-be-defined object. Now let's say there are 10 different types of forms. Can you do that with generics? A tree node, or it's a tree view that the nodes own a generic type, maybe is what he's trying to say?
Well, I'm also looking at it. He posted the question again. I think there's a little bit more detail there. If I wanted the tree view to own my forms, I would still have to cast them all to T form when I added them. Is this correct? Not necessarily. This is actually a really good question because it's one of the kind of fundamental decisions that always come up when you're trying to work with generics versus traditional object-oriented programming is, okay, when do I do a base class approach versus a generic? And in an example like this, since everything that's going to be managed by the node is a form of some kind, you could certainly use a base class approach where the node would have to be, some T form descendant. And maybe that's even a descendant of a T form that has specific characteristics. And then all 10 of the other forms would descend from that. That's a very old school, traditional, object-oriented way to deal with that. And that would work. Kind of the next level up for some added flexibility is using an interface for the various forms that you want, and your tree node is simply looking for an interface type that describes that, hey, I know what you minimally will support, so let me connect to you using just a straight interface. Switching it over to a generic, you could do it, but you're most likely going to want to use the constraints on the generic type parameter. And either say that it's a T custom form or a T form, some descendant, or even as one of the interfaces. And so in that case, you would hold that and make that work. However, the challenge that you're going to have is in how it's going to be used. When you deal with a generic, remember that you have to have to use it, you have to construct the generic type. You define it with the type parameter, then you have to construct it. Well, you construct it with one type. The tree node that you have in the list, you would define that as of type T or as of type some variant of T. With a constraint on it or whatever. All that would do is once you construct you don't individually construct the tree nodes in the tree view using different generic constructed types. I hope people can follow that and visualize that, because this is one of those little things to where as you start digging deeper, people tend to try to use generics in a way that isn't the best approach. And the likelihood is your tree view would hold different types of tree nodes. Now, if you want each of those to be an interface, then great, they can connect to other things, but you don't want to make it an absolute type, because then every tree node would have to be that type once you constructed the generic. So.
Okay, yeah, that makes sense, because, they'd all be the same type, so.
Which you may not want. I mean, then if it is going to be that way, you're better off with just a base class or an interface type directly, and I'm not sure what the generic is going to buy you unless you're creating different tree views that hold a specific kind of form, then hey, absolutely makes sense. Go ahead.
So Stefan wants to know if there's a reason you iterated over the keys property of the dictionary and then look up every value instead of iterating the values property.
You can do either one, more or less just to illustrate how you can do that. Typically, keys will be done in, you may iterate over the keys to sort it based on the keys and then extract the values out of it. And you have a lot of flexibility when dealing with the generics, or the generic dictionary, I mean. So.
If the generic can be anything, what is the best way to determine what specific type it is? RTTI? Is there a property on the generic or something else?
That's an interesting question, because my first gut reaction to that is, well, why do you care? Well, if the whole point of doing a generic is that your code should be type agnostic, if you will. You shouldn't worry about what the type is. If it is a concern, that's where you need to introduce the constraints so that you now handle it appropriately. If you're having to look at to find out what actual type is being used, I think you're going to run into problems where you're probably not using the generics in the way they're intended. I think I'd have to see a more precise example of what would be trying to accomplish, where you would try to get to the type. I mean, I know you can use the kind of the pseudo function for the default value, which internally figures that out, but that is only in a very rare case have I ever needed to worry about what real type has been substituted into the code.
Okay. Is there an example for the constructor constraint in a generic T sample of T : constructor?
I thought I put that in the one where I'm creating the different controls. Oh, sorry, that's in the RTTI session. Sorry, I have a lot of sessions in this conference. So tune in tomorrow to see something that's similar to that. So yeah, whenever you're going if you're going to create an instance of the type parameter that you're using, you obviously want to make sure that there's a constructor there so that you can actually create it. So in that case, doing T : of constructor makes sense when you're dealing with, say, you want to manage different controls or objects, customers, for example, and you want to be able to construct them dynamically. So your generic serves kind of as a factory in certain situations. Then you would want to be able to do that.
So Thomas wants to know, he says, I've heard that using generics can increase the size of your binary. Is there any way you can mitigate this, or is it just the way things are for now?
Well, the generics will, for each constructed type that you create, then the binary code has to get created for that constructed type. So if I have my T sample of T and I define that, and it does a bunch of stuff in the code, but then in my application code, when I use it, I have a T sample of integer and a T sample of string, then that basic code that was defined in the generic is going to be in the binary twice. So, is there anything that can be done to mitigate that? Not really. I mean, it's going to only create, duplicates code for what is being used. It's not like it's going through and doing it for all the types that is used by the application. Yeah, that's the only thing that I think any kind of comment on that. Typically, the benefit that you get from the flexibility and the code clarity and the simplification and keeping the type safety outweighs the extra code, the binary footprint that it's taking up.
Right. Well, and if you were to implement it without generics, then you'd have to define both a t-sample integer and a t-sample string type, and you'd end up creating the same amount of binary code probably and have twice as much text code as well.
Right.
So yeah. All right.
Well, yeah, the counter to that is, oh, well, then if I just make it, a very, I want to say generic, but a very basic, T object like structure where I don't care what's in it, or hey, I'll just make it a variant list. That has its downsides as well. You lose all the type safety, and you can get to some very hard to detect bugs when you do stuff like that.
Were constraints always part of generics, or is that something that's only in newer versions of Delphi?
Nope, that's been in there since the get-go. Although it is something that is not often, mentioned in some of the doc and the help. I mean, it's buried inside the help there, but you got to kind of look for it.
Okay. So Stefan's got a question that I guess probably not really for you to answer, but he wants to know if we're going to get generic method interfaces, which would be nice, but not currently available.
Yes, it would.
So we'll maybe can pass that along to product management. All right. Well, thank you, Ray, for another great session on generics in Object Pascal, effectively using generics in Object Pascal.